Let's show that the molar specific heat at constant pressure is connected to the molar specific heat at constant volume by the relation the molar specific heat at constant pressure is equal to the molar specific heat at constant volume plus the gas constant. Since we are dealing with pressure and volume processes and trying to connect them, we should start off with the PV diagram, which gives us a useful tool for connecting the two types of processes. The vertical axis is the pressure axis, the horizontal axis is the volume axis. We're trying to connect a process at constant pressure, so let's illustrate that. Here I will have a pressure P, starting off at a state A. Let's illustrate a constant pressure volume expansion. So at this pressure at point A with volume at A, let's illustrate an isobaric expansion to the same pressure but a different volume. We will call this second state, state B. We are also interested in a process at constant volume since we're trying to connect the two. So I'll illustrate a third state, C, at a higher pressure, P of C, but the same volume, V of A, for an isochoric pressure increase. So somehow we have to connect these two processes, the isobaric volume expansion and the isochoric pressure increase. To help us with this analysis, let's recognize that changes in thermal energy are directly proportional to temperature changes. So what this means is if we double our change of temperature, we double our thermal energy. If we triple our change of temperature, we triple our thermal energy. So for this, let's look at a change of temperature by illustrating two isotherms in our PV diagram. So one isotherm, let's have that going through our state A. We will call the temperature of this isotherm T of A. And then since our object starts off in state A with an initial pressure, with an initial volume, at an initial temperature of TA, let's illustrate a second isotherm that passes through both point C and point B. So being an isotherm, the temperature everywhere on this isotherm is constant. So the temperature at point B is equal to the temperature at point C. Now the reason why I'm connecting these two isotherms is to make use of the fact that I know changes of internal energy are directly proportional to temperature. So I wanted these two processes to have the same temperature change, such that the change of temperature from evolving from state A to B is equal to the change of temperature in evolving from state A to C. That's because we start off at point A on the isotherm TA and end up on the second isotherm. So the change in temperature between the two must be the same, and I'll indicate that by a delta T. So a couple of conceptual points to be mindful of. The change in thermal energy of a gas is the same for any two processes that have the same temperature change. So what that means is the change of internal energy in the process taking us from A to B must be equal to the change of internal energy in the process taking us from A to C, because the change of thermal energy is directly proportional to temperature change, and any two processes with the same temperature change must have the same change in internal energy. So we could use this fact and the first law of thermodynamics to connect our constant pressure process to our constant volume process. Remember, the first law of thermodynamics says that the change of thermal energy is equal to the heat exchanged by a system plus the work done by the environment on the system. So since we have two processes, let's look at the change of internal energy for process taking us from A to B. So this is going to be the heat exchange from A to B plus the work done by the environment on the system from A to B. Now this is equal to the change of internal energy from A to C, which is equal to the heat exchanged from A to C plus the work done by the environment on the system from A to C. Let's give ourselves more room to work by copying to the next page. So let's turn our attention now to this expression we have. The heat from A to B plus the work done from A to B equals the heat from A to C plus the work done from A to C. Now, we're trying to relate the specific heats at constant pressure to the specific heat at constant volume. So we could relate the two by just first looking at the heat terms. For the heat exchanged in the isobaric process from A to B, we know that that is directly proportional to the temperature change from A to B given by this molar specific heat capacity equation for the A to B process, which says the heat from A to B is equal to the number of moles times the molar specific heat capacity from A to B times the change of temperature from A to B. We can also determine an expression for the heat from A to C for the isochoric process, and that's given by the number of moles times the molar specific heat at constant volume, since it's an isochoric process, times the change of temperature from A to C. Now remember, the change of temperature from A to C is equal to the change of temperature from A to B. So we could write that the change of temperature, or the heat exchange from A to C, is equal to the number of moles times the molar specific heat at constant volume times the change of temperature from A to B. Now we have an expression for the heat exchange from A to B and the heat exchange from A to C in terms of temperature. Now let's see if we could come up with an expression for the work done from A to B and the work done from A to C. Let's start off with the easy one. Let's look at the work done from A to C. I know that the work done from A to C is going to be 0. You're probably wondering how I know that. Well, this is the usefulness of a PV diagram. It can tell us a lot of information with just some pictures. I know that work is represented in the PV diagram as the signed area between the PV curve and the volume axis. So for the A to C process, I see that there is 0 area under the vertical line connecting us to state A and state C. Since there is a zero area under that line, I know the work done from A to C must be equal to 0. So that allows us to eliminate the work done from A to C term in our previous expression. Now let's find the work done from A to B. Again, I know the work done between 2 points in a pressure volume diagram is equal to the negative of the signed area between the curve and the volume axis. So the work done from A to B is equal to minus the pressure. Pressure here is pressure at point A, which is the same as pressure at point B because it's an isobaric process, times the volume change. Now let's recognize the fact that the ideal gas law gives us a connection between pressure and volume and temperature. That the product of pressure and volume is equal to the number of moles times the gas constant times the temperature at a particular state. So if we look at the product of pressure and volume for state A, that's equal to nR temperature at state A. And if we look at the product of pressure and volume for state B, that is equal to nR temperature in state B. So combining these expressions allows me to write that the work done from A to B is equal to minus the pressure times the volume at state B plus the pressure times the volume at state A. Well, remember the pressure at state B is PB, pressure at state A is PA. So we could write that the work done from A to B is equal to, well here, the product of pressure and volume we had was nRTB plus nRTA for the product of pressure and volume for state A. So this allows me to write that the work done from A to B is equal to minus the number of moles times the gas constant times the temperature change from A to B. So let's remind ourselves of what we have. We have the heat exchange from A to B plus the work done from A to B is equal to the heat exchanged from A to C. We had that the heat exchange from A to B is equal to the number of moles times the molar specific heat at constant pressure times the change of temperature from A to B plus the work done from A to B, which we just showed to be equal to minus the number of moles times the gas constant times the temperature change from A to B. And that is equal to the heat exchange from A to C, which we found to be the number of moles times the molar specific heat at constant volume times the temperature change from A to C. Now, we're going to use the fact that the temperature change from A to B is equal to the temperature change from A to C, since we are going between the same two isotherms and the same two processes. What this allows us to do is to divide out the changes of temperature in every term. Also notice what we have is we have the same number of moles in every term, so we could divide those out as well. So rewriting our expression leaves us with the molar heat capacity at constant pressure minus the gas constant is equal to the molar heat capacity at constant volume. We did it. We found the relationship between pressure and volume for the molar heat capacities. While more traditionally, we tend to express this as a sum instead of a difference. So we could say the molar specific heat capacity at constant pressure is connected to the molar specific heat capacity at constant volume by the gas constant.